The universe is often described as a vast, mysterious expanse. But what if it's more like a cosmic symphony? A place where chaos and harmony dance in perfect balance, where the tiniest particles flicker unpredictably while galaxies spin in precise, breathtaking patterns. These hidden mechanisms, from the unpredictable swirls of quantum turbulence to the grand, ordered spirals of the cosmos, hold the keys to understanding the very fabric of reality. But here's the question: what if the universe isn't just random or orderly, but a delicate interplay of both? What if the turbulence we observe at the smallest scales is somehow connected to the vast, structured beauty we see in the stars? Today, we're diving deep into these mysteries, exploring how the chaotic and the cosmic are intertwined, and why unraveling these connections could change the way we see existence itself. From the mind-bending world of quantum mechanics to the awe-inspiring order of the universe, this journey will take you to the very edge of what we know and beyond. So, are you ready to uncover the hidden mechanisms that shape everything we see, and perhaps even what we don't? Let's begin. At the heart of the quantum realm lies a world that defies everything we think we know about reality. Here, particles don't behave like tiny billiard balls, neatly obeying the laws of classical physics. Instead, they flicker in and out of existence, appearing and vanishing in a dance of uncertainty. This is the quantum world, a place where chaos reigns but not without purpose. Imagine a storm at sea, waves crashing unpredictably, yet beneath the surface, there's a hidden rhythm, a pattern that governs the turbulence. This is quantum turbulence, a chaotic motion at microscopic scales that, despite its wild appearance, follows its own set of rules. Take superfluid helium, for instance. At temperatures close to absolute zero, this strange substance flows without friction, defying the rules of ordinary liquids. If you stir it, it doesn't slow down. Instead, it forms swirling vortices that move in a chaotic yet orderly fashion. Or consider Bose-Einstein condensates, where particles merge into a single quantum state, behaving as one entity. In these extreme conditions, quantum turbulence emerges, a state of chaos that's not random, but guided by unseen patterns. Why does this matter? Because these tiny, chaotic motions hold the key to understanding the universe's smallest scales. They reveal a hidden layer of reality, one where order and disorder are two sides of the same coin. But here's the fascinating part. The same chaotic patterns we see in quantum turbulence might echo in the vast structures of the cosmos. Could the swirling vortices of a superfluid be a microscopic reflection of the spiraling arms of a galaxy? It's a question that bridges the infinitesimal and the infinite, hinting at a deeper connection between the quantum realm and the cosmos. And that connection is where the true magic of the universe begins to unfold. Now, let's zoom out from the microscopic chaos of the quantum realm and into the staggering vastness of the cosmos. Here, amidst the endless expanse of space, we find a structure so immense it defies comprehension: the cosmic web. Picture this: a sprawling network of galaxies, gas, and dark matter, stretching across billions of light years, forming an intricate tapestry of filaments, voids, and clusters. It's a structure so vast that our own Milky Way is just one tiny thread in this grand design. At first glance, the cosmic web might seem like pure chaos, a random scattering of light across the void. But look closer, and you'll see an astonishing order. Gravity, the universe's great architect, has been at work here, pulling matter together over billions of years to weave this intricate pattern. Galaxies cluster along gossamer filaments like beads on a string, while vast voids stretch between them, empty and dark. It's a cosmic dance of attraction and repulsion, of matter gathering and emptiness expanding. To grasp the scale, think of a spider's web glistening with dew in the morning light. Each strand is delicate, yet together they form a structure of incredible strength and precision. Or consider the neural networks in our brains, where billions of connections create the foundation of thought and consciousness. The cosmic web is nature's ultimate network, a blueprint of order on a scale so vast it's almost impossible to fathom. But here's where it gets even more intriguing. While the cosmic web represents order on a grand scale, it's not entirely separate from the chaos we see in the quantum realm. The same forces that govern the swirling vortices of quantum turbulence, gravity, energy, and the fundamental laws of physics are also at work here, shaping the universe on the largest scales. Could it be that the chaotic dance of particles at the quantum level is somehow mirrored in the ordered structure of the cosmic web? This idea isn't just poetic, it's a question scientists are actively exploring. The filaments of the cosmic web, for instance, might trace their origins back to quantum fluctuations in the early universe, tiny ripples that grew into the vast structures we see today. It's a connection that bridges the smallest and largest scales, hinting at a deeper unity in the fabric of reality. So, as we stand between these two extremes, the chaotic whirl of quantum turbulence and the majestic order of the cosmic web, we begin to see the universe not as a collection of separate phenomena, but as a single, interconnected whole. And it's this connection that might hold the key to understanding not just how the universe works, but why it works the way it does, but what holds this cosmic web together. What unseen hands guide the dance of galaxies and the vast voids between them? The answer lies in two of the universe's greatest mysteries, dark matter and dark energy. Together, they form the invisible scaffolding of the cosmos, shaping everything from the smallest filaments of the cosmic web to the universe's accelerating expansion. Let's start with dark matter. Unlike ordinary matter, the stuff that makes up stars, planets, and everything we can see, dark matter doesn't emit, absorb, or reflect light. It's completely invisible, yet its presence is undeniable. How? Through gravity. Dark matter's gravitational pull is what binds galaxies together, preventing them from flying apart as they spin. It's also what forms the cosmic web, creating the massive structures that stretch across the universe. Think of it like the hidden framework of a building. You can't see it, but without it, the entire structure would collapse. Then there's dark energy, an even more enigmatic force. While dark matter pulls things together, dark energy pushes them apart. It's the reason the universe isn't just expanding, it's expanding faster and faster, as if some invisible hand is constantly pressing the accelerator. Scientists believe dark energy makes up about 68% of the universe's energy content. But what it actually is remains one of the biggest questions in physics. Here's where things get even more intriguing. Even though we can't see dark matter or dark energy directly, we can observe their effects. For example, galaxies rotate faster than they should based on the visible matter alone, suggesting the presence of dark matter. And the cosmic microwave background, the faint glow left over from the Big Bang, shows patterns that only make sense if dark energy is at work. As physicist Vera Rubin once said, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined." But why can't we detect these forces directly? Part of the challenge is that dark matter doesn't interact with light or ordinary matter in any way we can easily measure. It's like trying to catch a shadow with your bare hands, and dark energy, it's even more elusive, acting on scales so vast that its effects are only noticeable over billions of years. So, where does quantum physics fit into all this? Could the tiny, chaotic world of particles hold clues about the nature of dark matter and dark energy? Some scientists think so. For instance, certain theories suggest that dark matter might be made up of particles that interact through quantum forces we don't yet understand. Others propose that dark energy could be linked to fluctuations in the quantum vacuum, the seething sea of energy that permeates empty space. These ideas are still speculative, but they highlight an exciting possibility that the quantum realm and the cosmos might not just be connected, they might be two sides of the same cosmic coin. As we continue to explore these hidden forces, one thing becomes clear: the universe is far stranger and more interconnected than we ever imagined. And it's this interplay between the seen and the unseen, the chaotic and the ordered, that keeps us searching, wondering, and uncovering the secrets of existence itself. Now, let's step back in time, way back, to the very beginning of the universe. In those first fleeting moments, the cosmos was a seething cauldron of energy, a place where the rules of quantum mechanics held sway. And in that chaos, something extraordinary happened. Tiny, random fluctuations arose in the quantum fabric of reality. These were no ordinary ripples, they were the seeds of everything we see today. Picture this: a perfectly calm pond on a windless day. Now, imagine dropping a single pebble into its center. The ripples that spread outward are small at first, barely noticeable. But over time, they grow, shaping the surface of the water in patterns that grow larger and more complex. In the early universe, something similar occurred. Quantum fluctuations, tiny, unpredictable variations in energy, were stretched to unimaginable scales during a period known as inflation. In less than a blink of an eye, the universe expanded faster than the speed of light, magnifying those minuscule ripples into cosmic waves. These waves weren't just random noise, they carried the first hints of structure. As the universe cooled and matter began to form, those amplified quantum ripples became the blueprint for galaxies, clusters, and the vast filaments of the cosmic web. Think of it like a baker kneading dough. The initial imperfections, the tiny air pockets, grow as the dough rises, shaping the final loaf. In the same way, those early quantum fluctuations set the stage for the universe's grand architecture. This connection between the quantum world and the cosmos is more than just a fascinating idea. It's a cornerstone of modern cosmology. Scientists have even detected echoes of these ancient quantum ripples in the cosmic microwave background, the faint afterglow of the Big Bang. These subtle temperature variations, imprinted on the fabric of space-time, are like cosmic fingerprints, revealing the universe's quantum origins. But what does this mean for our understanding of existence? It suggests that the universe is built on a foundation of both randomness and order. The same quantum uncertainty that makes particles flicker in and out of existence also gave rise to the galaxies and stars that light up the night sky. It's a profound reminder that chaos and structure aren't opposites, they're partners in the cosmic dance. As we piece together this story, we're left with a tantalizing question. Could the universe itself be a quantum phenomenon on an unimaginably vast scale? The answer might lie in the intricate interplay between the smallest particles and the largest structures, a connection that continues to challenge and inspire us. And as we unravel these mysteries, we're not just learning about the universe, we're discovering how deeply intertwined it is with the very fabric of reality itself. What if everything we see, stars, galaxies, even the fabric of space itself, isn't quite what it seems? What if the universe is like a hologram, a three-dimensional projection of information stored on a two-dimensional surface? This is the essence of the holographic principle, a radical idea that turns our understanding of reality on its head. At its core, this principle suggests that the universe's vast complexity, everything from the motion of planets to the flicker of quantum particles, could be encoded on a flat, boundary-like surface, like a cosmic DVD containing the information needed to reconstruct the entire three-dimensional world. To grasp this concept, think of a hologram you might see on a credit card or a concert ticket. Even though it's a flat surface, it creates the illusion of depth, a three-dimensional image that changes as you move. Now, imagine that on a cosmic scale, the holographic principle proposes that the universe itself might work in a similar way. All the information about every particle, every force, every event in the cosmos could be stored on a two-dimensional surface at the edge of the universe. What we perceive as three-dimensional reality might just be the projection of that information. This idea didn't come out of thin air. It emerged from the study of black holes, those enigmatic regions of space where gravity is so strong that not even light can escape. Physicist Leonard Susskind, one of the pioneers of this theory, realized that the information swallowed by a black hole isn't lost forever. Instead, it's somehow encoded on the black hole's event horizon, the two-dimensional boundary that marks the point of no return. This discovery led to a startling conclusion. If information can be stored on a two-dimensional surface for a black hole, why not for the entire universe? The implications of this principle are profound. For one, it challenges our traditional notions of space and time. We're used to thinking of the universe as a three-dimensional stage where events unfold over time. But if the holographic principle is correct, space and time might not be fundamental. Instead, they could emerge from something deeper, a web of information encoded on a two-dimensional surface. This idea also offers a potential bridge between two of physics' greatest theories, quantum mechanics and general relativity. Quantum mechanics governs the behavior of the very small, while general relativity explains the very large, like the curvature of space-time around massive objects. These two theories have been notoriously difficult to reconcile, but the holographic principle suggests a way forward. By treating space and time as emergent properties of a deeper, information-based reality, it provides a framework where both quantum mechanics and general relativity could coexist. So, how might this principle explain the hidden mechanisms of the universe? Consider the cosmic web, that vast network of galaxies and filaments stretching across the cosmos. If the universe is holographic, the information encoding this structure might reside on a two-dimensional surface at its boundary. The intricate patterns we see, galaxies clustering along filaments, voids stretching between them, could be the three-dimensional projection of that information. This isn't just a theoretical curiosity, it's a bold new way of thinking about reality. As physicist Juan Maldacena once put it, the holographic principle suggests that the universe is a kind of cosmic code, and we're just beginning to crack it. It's a reminder that the universe is far stranger and more interconnected than we ever imagined, and that the answers to some of our biggest questions might lie in the most unexpected places. As we continue to explore this idea, we're not just uncovering the secrets of the cosmos, we're redefining what it means to exist within it. The holographic principle invites us to see the universe not as a collection of separate parts, but as a unified whole, where the smallest particles and the largest structures are intimately connected. And in that connection, we might just find the key to understanding the hidden mechanisms that shape everything we know and everything we don't. Now, let's shift our focus to one of the most mind-bending phenomena in the quantum world, entanglement. Imagine two particles, separated by vast distances millions of light years, even yet somehow they remain intimately connected. Change the state of one, and the other instantly responds, as if they share an invisible thread that defies the limits of space and time. This is quantum entanglement, a phenomenon so strange that even Albert Einstein famously called it spooky action at a distance. To understand entanglement, picture a pair of dice. If you roll one in New York and the other in Tokyo, you'd expect the results to be completely independent, right? But in the quantum world, entangled particles are like dice that always land on matching numbers, no matter how far apart they are. This connection isn't just a theoretical curiosity, it's been proven through experiments time and time again. In one famous example, known as the Fermi Paradox, physicists Albert Einstein, Boris Podolsky, and Nathan Rosen tried to argue that quantum mechanics couldn't possibly be complete because it allowed for such bizarre connections. Yet, decades later, experiments like those by John Bell confirmed that entanglement is very real and very strange. Recent breakthroughs have taken this phenomenon to new extremes. Scientists have successfully entangled particles over distances of more than 1,000 kilometers, using satellites to send entangled photons across continents. These experiments aren't just scientific feats, they're windows into a deeper truth about the universe, that connections can exist beyond the reach of space and time as we know them. But what does this mean for the cosmos? Could entanglement play a role in the universe's grand structures, like the cosmic web? Some researchers think so. Just as entangled particles remain linked across vast distances, the filaments and clusters of the cosmic web might be held together by a kind of cosmic entanglement, a network of connections that transcends the visible. This idea is still speculative, but it offers a tantalizing possibility that the universe isn't just a collection of separate objects, but a deeply interconnected whole. Think of it like this: if entanglement can link particles instantaneously, perhaps it also weaves the fabric of reality itself, from the smallest scales of quantum physics to the vast expanse of the cosmos. This phenomenon hints at a level of unity that challenges our everyday understanding of how things work. Could entanglement be one of the hidden mechanisms that binds the universe together? As we explore this question, we're reminded that the universe is far more mysterious than it appears. Entanglement isn't just a quirk of the quantum realm, it's a clue to the profound interconnectedness of all things. And as we uncover more about this strange and beautiful phenomenon, we're not just learning about the universe, we're glimpsing the invisible threads that tie it all together. What if our universe isn't the only one? What if beyond the stars and galaxies we can see, there are countless other universes, each with its own unique set of physical laws, its own history, and perhaps even its own version of reality? This is the Multiverse Theory, a bold and provocative idea that suggests our cosmos is just one bubble in a vast cosmic foam, where each bubble represents a separate universe. The concept of the multiverse isn't just science fiction. It emerges from some of the most robust theories in modern physics, including quantum mechanics and cosmic inflation. Let's start with inflation, the rapid expansion of the universe in its earliest moments. According to this theory, the universe didn't just inflate once, it could have done so endlessly, creating pockets of space-time that eventually became their own universes. Picture a pot of boiling water where bubbles constantly form, rise to the surface, and float away. In the same way, our universe might be just one bubble in an infinite sea of others, each with its own distinct properties. Quantum mechanics adds another layer to this idea. At the quantum level, particles exist in a state of probability, meaning they can occupy multiple states simultaneously until observed. This principle, known as superposition, suggests that every possible outcome of a quantum event actually occurs. Somewhere, in the multiverse framework, each of these outcomes could spawn a new universe, branching off from our own. It's like a cosmic tree with infinite branches, each representing a different path reality could have taken. But what does this mean for the hidden mechanisms of the universe? If the multiverse is real, it could explain some of the most puzzling features of our cosmos. For instance, why are the fundamental constants of nature, like the speed of light or the strength of gravity, so finely tuned to allow for the existence of life? In a multiverse, every possible set of physical laws exists somewhere, and we just happen to live in the universe where those laws are just right for us. It's like winning the cosmic lottery, where the odds are astronomically low, but with infinite universes, someone had to hit the jackpot. This idea also challenges our understanding of cosmic order. If there are infinite universes, does order even exist, or is it just a matter of perspective? In some universes, chaos might reign supreme, while in others, the laws of physics could create structures even more intricate than our cosmic web. The multiverse forces us to reconsider not just the scale of existence, but the very nature of reality itself. So, how might the multiverse influence our perception of the universe's hidden mechanisms? If the cosmos is just one thread in an infinite tapestry, then the patterns we observe, from quantum turbulence to the cosmic web, might be just one expression of a much deeper truth. The multiverse invites us to think beyond the boundaries of our own universe, to imagine a reality where the rules we take for granted are just one possibility among countless others. As we explore this idea, we're reminded that the universe, or universes, is far more complex and mysterious than we can ever fully grasp. The multiverse theory doesn't just expand our horizons, it transforms the way we see existence itself. And in that transformation, we might just find the key to unlocking the deepest secrets of the cosmos. Black holes are often portrayed as cosmic monsters, devouring everything in their path: light, stars, even time itself. But what if they're more than just destructive forces? What if they're gateways to some of the universe's deepest secrets? These enigmatic regions of space are where the two great pillars of modern physics, quantum mechanics and gravity, meet head-on, creating a collision of ideas that challenges everything we think we know about reality. At the heart of a black hole lies the singularity, a point where gravity becomes infinitely strong, warping space and time beyond recognition. Surrounding it is the event horizon, a boundary so strange that nothing, not even light, can escape once it crosses. To visualize this, imagine a cosmic whirlpool, where the water spirals inward faster and faster until it vanishes into a hidden depth. In the same way, a black hole pulls everything into its grasp, creating a one-way street into the unknown. But here's where things get even more fascinating. In the 1970s, physicist Stephen Hawking made a startling discovery: black holes aren't entirely black. According to his calculations, they emit a faint glow of radiation, now known as Hawking radiation. This phenomenon occurs because of quantum effects near the event horizon, where pairs of particles spontaneously pop into existence. Normally, these particles annihilate each other almost instantly, but near a black hole, one particle can fall in while the other escapes, carrying away energy. Over time, this process causes the black hole to slowly evaporate, shrinking until it vanishes entirely. This discovery raised a profound question: What happens to the information about the objects that fall into a black hole? According to quantum mechanics, information can never be destroyed. It's a fundamental law of the universe. But if a black hole evaporates, leaving no trace of what it consumed, where does that information go? This is the information paradox, a puzzle that has stumped physicists for decades. Some theories suggest that the information might be encoded on the event horizon, like a cosmic hard drive storing the universe's data. Others propose that it's hidden in the radiation itself, scrambled beyond recognition. And then there's the holographic principle, which we explored earlier, suggesting that the information might be projected onto a two-dimensional surface at the black hole's boundary. These ideas aren't just abstract musings, they're attempts to reconcile the quantum world with the gravitational forces that dominate black holes. But why does this matter? Because black holes aren't just isolated oddities, they're windows into the universe's hidden mechanisms, the way they warp space and time, the way they interact with quantum particles, and the way they challenge our understanding of information. All of these offer clues about the deeper nature of reality. They force us to ask questions we might never have considered. Is space-time smooth or granular at the smallest scales? Can information truly be lost, or is it just hidden in ways we don't yet understand? As we peer into these cosmic whirlpools, we're reminded that the universe is far stranger than it appears. Black holes aren't just gateways to hidden realms, they're mirrors reflecting our own limitations, showing us how much we still have to learn. They challenge us to think bigger, to explore further, and to unravel the mysteries that lie at the intersection of the quantum and the cosmic. And in that challenge, we might just find the keys to understanding the universe's most profound secrets. Time is one of the most familiar yet mysterious aspects of our existence. We experience it as a one-way street, always moving forward, never backward. But why does time flow in this direction? What gives it its arrow? The answer lies in a concept that shapes not just our daily lives but the entire universe: entropy. Entropy is a measure of disorder, and it's one of the few physical quantities that gives time its direction. Think of a sandcastle on a beach. Left to itself, it doesn't stay perfectly sculpted. It crumbles, scattering grains of sand in all directions. That's entropy at work, increasing disorder over time. In the universe, this principle operates on a cosmic scale. From the chaotic swirls of quantum turbulence to the vast, ordered structures of galaxies, entropy is the force that drives the universe's evolution. Let's rewind to the very beginning, the Big Bang. At that moment, the universe was in a state of near-perfect order, a hot, dense soup of particles packed tightly together. But as the universe expanded and cooled, entropy began to rise. The once uniform energy spread out, forming the seeds of structure, tiny ripples that would grow into galaxies, stars, and planets. This transformation from order to disorder might seem counterintuitive, but it's the key to understanding how complexity emerges in the cosmos. Now, fast forward to the far future. Scientists predict a state known as the heat death of the universe, where entropy reaches its maximum. In this distant era, stars will have burned out, galaxies will have drifted apart, and the universe will become a vast, cold expanse of evenly distributed energy. It's a stark contrast to the vibrant, dynamic cosmos we see today, but it's the natural endpoint of entropy's relentless march. So how does this connect to the hidden mechanisms of the universe? Entropy isn't just a passive force, it's an active participant in shaping reality. It's what allows energy to flow, driving processes like the formation of stars, the birth of planets, and even the emergence of life. Without entropy, the universe would be stuck in a static, unchanging state, a cosmic standstill. But here's the intriguing twist. While entropy increases on a cosmic scale, it also creates pockets of order. Think of a snowflake forming in a storm. The overall system, the storm, is chaotic, but within it, intricate patterns emerge. In the same way, the universe's increasing entropy has given rise to the stunning complexity we see around us, from the spiraling arms of galaxies to the delicate balance of ecosystems on Earth. This interplay between chaos and order isn't just a cosmic quirk, it's a fundamental feature of reality. The arrow of time, driven by entropy, connects the quantum realm to the cosmos, the Big Bang to the heat death, and the hidden mechanisms that shape everything in between. It's a reminder that even in a universe tending toward disorder, beauty and structure can flourish, a testament to the delicate balance that defines existence itself. As we reflect on this journey through time and entropy, we're left with a profound question. What does it mean for the universe to have a direction, a purpose, even if that purpose is simply to evolve? The answer might lie in the intricate dance of chaos and order, a dance that continues to unfold with every passing moment. And in that unfolding, we find not just the story of the universe, but the story of ourselves. Symmetry is often associated with beauty and balance, a perfectly mirrored reflection, a snowflake's intricate design, or the graceful spiral of a galaxy. But in the universe, symmetry is far more than just an aesthetic principle. It's a fundamental force that shapes the very fabric of reality. From the tiniest particles to the vastest cosmic structures, symmetry plays a crucial role in how the universe works and how it came to be. At its core, symmetry in physics refers to the idea that certain properties remain unchanged even when conditions shift. Picture a spinning top. No matter how it rotates, it looks the same from every angle. This kind of invariance is what physicists call symmetry, and it's a cornerstone of the laws that govern the universe. But here's the twist. While symmetry is essential, it's the breaking of symmetry that often drives the most dramatic changes. Consider the early universe, a place of unimaginable energy and heat. In those first moments, everything was perfectly symmetrical, a uniform, featureless soup of particles and forces. But as the universe expanded and cooled, that symmetry began to break, like a frozen lake cracking under the weight of its own ice. This process, known as spontaneous symmetry breaking, is what allowed structures to form. One of the most famous examples of this is the Higgs field. In the early universe, this field was perfectly symmetrical, but as temperatures dropped, it shifted, creating a kind of cosmic tilt. This tilt gave mass to certain particles, like the W and Z bosons, while leaving others, like photons, massless. It's this broken symmetry that explains why some particles have mass and others don't, and why we exist at all. Without it, the universe would be a very different place, devoid of the complexity we see today. But symmetry breaking isn't just a quantum phenomenon, it's also at work on cosmic scales. Think of water freezing into ice. As the temperature drops, the water molecules shift from a chaotic, symmetrical state to an orderly, crystalline structure. This phase transition is a form of symmetry breaking, and it's eerily similar to what happened in the early universe. The same principles that turn water into ice also shaped the cosmic web, transforming a uniform sea of energy into the intricate network of galaxies and filaments we observe today. What's fascinating is how these broken symmetries connect the quantum realm to the cosmos. In both cases, the transition from symmetry to asymmetry creates the conditions for complexity to emerge. The Higgs field's broken symmetry gave rise to the particles that make up matter, while cosmic symmetry breaking laid the groundwork for the universe's grand structures. It's a reminder that the same fundamental principles operate at every scale, from the smallest particles to the largest galaxies. So, what does this mean for our understanding of the universe? Symmetry and its breaking reveal a hidden order behind the apparent chaos. They show us that the universe isn't just a random collection of events, but a system governed by deep, underlying patterns. And as we uncover these patterns, we're not just learning about the universe's past, we're glimpsing the mechanisms that continue to shape its future. This interplay between symmetry and asymmetry is one of the most profound ideas in physics, bridging the quantum and the cosmic in ways we're only beginning to understand. It's a testament to the universe's elegance and complexity, a reminder that even in the smallest disruptions, there's a beauty that connects everything together. And in that connection, we might just find the key to understanding the universe's most profound secrets. The standard model of particle physics is often described as one of humanity's greatest intellectual achievements, a framework that explains how the fundamental building blocks of the universe interact. It's like a beautifully crafted puzzle, where each piece represents a particle or force, fitting together to reveal a coherent picture of reality. But here's the catch: even the most complete puzzles sometimes have missing pieces, and the standard model is no exception. At its core, the standard model describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, and the particles that mediate them. Quarks, electrons, neutrinos, and photons are just a few of the characters in this cosmic drama. Together, they form the basis of everything we see, from the atoms in our bodies to the light from distant stars. The model has been incredibly successful, predicting the existence of particles like the Higgs boson long before they were discovered. It's a testament to the power of human ingenuity, a tool that has unlocked countless secrets of the quantum realm. Yet for all its triumphs, the standard model isn't without its limitations. One glaring omission is gravity, the force that shapes galaxies and bends the fabric of space-time. While the model explains the other three forces with remarkable precision, gravity remains outside its scope, governed by Einstein's theory of general relativity. This disconnect between the quantum world and gravity is one of the biggest unsolved problems in physics, a gap that hints at a deeper, more unified theory waiting to be discovered. Another mystery the standard model can't explain is dark matter. Despite making up roughly 27% of the universe's mass energy content, dark matter doesn't fit into the model's framework. It doesn't interact with light or ordinary matter in any way the model accounts for, leaving scientists to wonder if entirely new particles or forces are at play. It's like trying to solve a puzzle with pieces that don't quite fit, a challenge that pushes the boundaries of our understanding. So, where does the standard model fit into the broader picture of cosmic order? Think of it as a snapshot of reality, capturing the most essential features of the universe, but leaving some corners of the frame empty. It's a tool that has brought us closer to understanding the quantum world, yet it also reminds us how much we still have to learn. As we explore this framework, we're left with a tantalizing question. Could the missing pieces of the standard model, gravity, dark matter, and perhaps even dark energy, be connected in ways we haven't yet imagined? The answer might lie in a deeper, more unified theory, one that bridges the quantum and the cosmic, the known and the unknown. And in that pursuit, we're not just solving a puzzle, we're uncovering the hidden mechanisms that shape the universe itself. Imagine the universe as a grand orchestra, where every particle, every force, and every cosmic structure plays its part in a symphony of unimaginable complexity. Now, what if the musicians in this orchestra weren't individual players but tiny, vibrating strings, each resonating at a unique frequency to create the harmonies of existence? This is the essence of string theory, a bold and ambitious attempt to unify the two great pillars of modern physics, quantum mechanics and general relativity. At its core, string theory proposes that the fundamental building blocks of the universe aren't point-like particles, as the standard model suggests, but minuscule, one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a violin, producing the diverse array of particles and forces we observe. A string vibrating one way might give rise to an electron, while another vibration could create a photon. In this framework, everything, from the tiniest quark to the vastest galaxy, emerges from the interplay of these cosmic strings. The implications of this idea are profound. For decades, physicists have struggled to reconcile quantum mechanics, which governs the behavior of the very small, with general relativity, which explains the very large. Quantum mechanics describes a world of probabilities and uncertainties, while general relativity paints a picture of smooth, curved space-time. String theory offers a potential bridge between these two worlds, suggesting that the fabric of reality itself might be woven from these vibrating strings. But string theory doesn't stop there. It also introduces the idea of extra dimensions, hidden layers of reality, beyond the three spatial dimensions we experience. In some versions of the theory, the universe has 10 or even 11 dimensions, with the extra dimensions curled up so tightly that we can't perceive them directly. Think of it like a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a circular dimension wrapped around it. These hidden dimensions could hold the key to understanding the universe's deepest mysteries, from the nature of gravity to the existence of dark matter and dark energy. Despite its elegance, string theory isn't without its challenges. For one, it's incredibly difficult to test experimentally. The strings themselves are thought to be so small, far smaller than an atom, that detecting them directly is beyond our current technological capabilities. Additionally, the theory comes in multiple versions, each with its own set of equations and predictions, leaving physicists to wonder which, if any, might describe our universe. Yet, even with these hurdles, string theory continues to inspire. It offers a vision of a unified reality, where the chaotic quantum world and the ordered cosmos are two sides of the same coin. It suggests that the universe's hidden mechanisms, from the flicker of particles to the curvature of space-time, might all be part of a single, elegant framework. As we explore this idea, we're reminded that science is as much about asking questions as it is about finding answers. String theory invites us to imagine a universe where the smallest vibrations create the grandest symphonies, where the boundaries between the quantum and the cosmic blur into a single, harmonious whole. And in that vision, we might just glimpse the ultimate truth of how everything fits together. 13.8 billion years ago, the universe as we know it burst into existence in an event so monumental, so explosive, that its echoes still reverberate through the cosmos today. This was the Big Bang, the universe's turbulent birth, a moment when all of space, time, and energy erupted from a single, unimaginably dense point. But what does it mean for the universe to have a beginning? And how did this explosive event set the stage for everything we see around us? To grasp the scale of the Big Bang, imagine a cosmic fireworks display on the grandest possible scale. In an instant, a singularity, a point of infinite density and temperature expanded faster than the speed of light, unfurling space and time like a cosmic tapestry. This wasn't just an explosion of matter, it was the birth of reality itself. As the universe expanded and cooled, particles began to form, and the first seeds of structure emerged. But here's the fascinating part. Even in that chaotic maelstrom, there was a hidden order. Quantum fluctuations, those tiny ripples of uncertainty in the fabric of reality, played a crucial role in shaping the universe's destiny. Picture a calm lake suddenly disturbed by a strong wind. The surface ripples, creating patterns that grow and spread. In the early universe, quantum fluctuations acted like those ripples, imprinting the cosmos with subtle variations in density. Over billions of years, these variations grew under the influence of gravity, forming the first galaxies, stars, and planets. The evidence for the Big Bang is overwhelming. One of the most compelling pieces is the cosmic microwave background radiation, a faint glow that fills the universe. This radiation is like a cosmic photograph, capturing the universe just 400,000 years after the Big Bang, when it had cooled enough for light to travel freely. The patterns in this radiation, tiny temperature fluctuations, match the predictions of quantum fluctuations in the early universe, providing a direct link between the quantum realm and the cosmos we see today. But the Big Bang isn't just a story about the past. It's a window into the universe's hidden mechanisms. The quantum fluctuations that shaped the cosmos also laid the groundwork for its complexity and diversity. Without those tiny ripples, the universe might have remained a featureless sea of particles, devoid of the galaxies, stars, and planets that make it so breathtakingly beautiful. As we explore this explosive beginning, we're reminded that the universe is a dynamic, evolving entity, shaped by both chaos and order. The Big Bang wasn't just a one-time event, it was the first act in an ongoing cosmic drama, a story that continues to unfold with every passing moment. And in that story, we find not just the origins of the universe, but the seeds of its future, a future that we're only beginning to understand. Now, let's zoom in on one of the most extraordinary chapters in the universe's story, cosmic inflation. Picture the universe in its earliest moments, a fraction of a second after the Big Bang. Instead of expanding at a steady pace, space itself underwent an explosive growth spurt, stretching faster than the speed of light. This wasn't just a gentle stretching, it was a cosmic sprint, inflating the universe from something smaller than an atom to something trillions of times larger in less than a blink of an eye. To grasp this, think of a balloon being blown up. When you start, the balloon is tiny, but as air rushes in, it expands rapidly, its surface stretching in all directions. Cosmic inflation was like that, except instead of air, it was the fabric of space itself expanding, carrying everything within it along for the ride. This rapid expansion didn't just make the universe bigger, it also smoothed it out, ironing out any wrinkles or irregularities. That's why the universe looks so remarkably uniform on large scales, with galaxies and clusters distributed evenly across the cosmos. But inflation wasn't just about smoothing things out, it also planted the seeds for the universe's structure. During this rapid expansion, tiny quantum fluctuations, those unpredictable ripples in the fabric of reality, were stretched to cosmic proportions. Imagine drawing a tiny dot on a deflated balloon. As you blow it up, the dot grows into a much larger pattern. In the same way, the quantum fluctuations of the early universe were magnified, becoming the blueprint for galaxies, stars, and the cosmic web we see today. This connection between quantum turbulence and cosmic structure is one of the most profound ideas in modern cosmology. It suggests that the chaotic flicker of particles at the smallest scales is intimately linked to the vast, ordered patterns of the cosmos. In a way, the universe's grand design might have been written in the language of quantum mechanics, with inflation acting as the translator, turning microscopic chaos into cosmic order. So, how does this tie back to the hidden mechanisms of the universe? Inflation isn't just a theory about the past, it's a key to understanding the present. It explains why the universe looks the way it does, from its uniformity to its intricate structures. But it also raises new questions. What triggered inflation? What caused it to stop? And could quantum turbulence hold the answers to these mysteries? As we explore these questions, we're reminded that the universe is a place of both chaos and harmony, where the smallest events can have the largest consequences. Cosmic inflation is a reminder that even in the most explosive moments, there's a hidden order, a thread that connects the quantum realm to the cosmos. And in that connection, we might just find the keys to understanding the universe's deepest secrets. Now, let's turn our attention to one of the most remarkable discoveries in modern cosmology, the cosmic microwave background, or CMB. This faint glow, invisible to the naked eye, is a treasure trove of information, a cosmic echo from the universe's infancy, a whisper from the moment light first broke free. It's like stumbling upon an ancient photograph, perfectly preserved, capturing the universe in its earliest moments. The CMB is often described as the afterglow of the Big Bang, but it's far more than that. It's a snapshot of the universe when it was just 400,000 years old, a time when it had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely for the first time. This light has been traveling through space ever since, stretched by the expansion of the universe into the microwave wavelengths we detect today. What makes the CMB so extraordinary is the level of detail it contains. Imagine a fingerprint unique, intricate, and revealing. The CMB is like a cosmic fingerprint, carrying imprints of the quantum fluctuations that shaped the early universe. These tiny ripples, magnified by cosmic inflation, became the seeds of all structure in the cosmos. The slightly denser regions grew into galaxies and clusters, while the less dense areas became the vast voids we see today. In this way, the CMB isn't just a relic of the past, it's a blueprint for the universe's evolution. But how do we decode this cosmic message? Scientists use incredibly sensitive instruments, like the Planck satellite, to map the CMB's temperature variations, tiny differences, just a few millionths of a degree, that reveal the density fluctuations of the early universe. These variations are like the brushstrokes of a cosmic artist, painting the first outlines of what would become the universe's grand structures. What's even more fascinating is how the CMB connects the quantum realm to the cosmos. Those tiny quantum fluctuations, born in the universe's first moments, were stretched to cosmic scales by inflation, leaving their mark on the CMB. This means that when we study the CMB, we're not just looking at the universe's past, we're peering into the quantum origins of reality itself. The CMB also offers a window into the universe's hidden mechanisms. For instance, it provides crucial evidence for dark matter and dark energy, the mysterious forces that shape the cosmos. The patterns in the CMB's temperature fluctuations align with predictions made by models that include these invisible components, helping us refine our understanding of their roles. As we explore this cosmic fingerprint, we're reminded that the universe is a deeply interconnected system, where the smallest events can have the largest consequences. The The CMB isn't just a relic of the Big Bang, it's a testament to the universe's unity, a reminder that the quantum and the cosmic are threads in the same cosmic tapestry. And as we continue to decode its secrets, we're not just uncovering the past, we're unraveling the hidden mechanisms that shape everything we see. What if the universe wasn't just random? What if its fundamental constants, the speed of light, the strength of gravity, the mass of an electron, were precisely tuned to allow life to exist? This is the fine-tuning problem, one of the most intriguing and debated questions in modern science. It suggests that the universe's laws and constants aren't arbitrary. They seem to be calibrated with astonishing precision, as if designed to create the conditions necessary for life. Think of it like a cosmic dial. Imagine turning a knob that controls the strength of gravity. Turn it slightly one way, and stars might never form. Turn it the other way, and galaxies could collapse too quickly. Now, consider that this dial isn't just set to any value, it's set to the exact number that allows stars, planets, and ultimately, life to emerge. This delicate balance isn't limited to gravity. Nearly every constant in the universe, from the charge of an electron to the density of dark energy, appears to fall within a narrow range that makes life possible. So, how do we explain this? One idea is the Anthropic Principle, which suggests that the universe's constants are the way they are because if they weren't, we wouldn't be here to observe them. It's a self-selecting argument. The universe must be fine-tuned because we exist to notice it. But this raises deeper questions. Is fine-tuning just a cosmic coincidence, or does it point to something more profound? Another possibility is the multiverse. If our universe is just one of countless others, each with its own set of physical laws, then it's no surprise that at least one would have the right conditions for life. In this scenario, we're not special, we're just lucky. Like winning the cosmic lottery, our universe hit the jackpot, while countless others remain barren and lifeless. But here's where it gets even more fascinating. Fine-tuning isn't just a philosophical puzzle, it's deeply connected to the universe's hidden mechanisms. The same forces that govern quantum fluctuations and cosmic inflation, the ones that shaped the early universe, could also explain why the constants are so finely balanced. For instance, if the Higgs field had a slightly different value, atoms might not have formed, and the universe would be a sea of featureless energy. This interplay between fine-tuning and hidden mechanisms invites us to think bigger. Could the universe's constants be the result of deeper, underlying laws we haven't yet discovered? Are they the product of a grand cosmic equation waiting to be solved? Or is fine-tuning evidence of something even more extraordinary, a universe that's not just random, but imbued with purpose? As we explore these questions, we're reminded that the universe is a place of both mystery and meaning. The fine-tuning problem doesn't just challenge our understanding of physics, it invites us to reflect on our place in the cosmos. Are we here by chance, or is there something more to the story? And as we search for answers, we might just uncover the hidden mechanisms that make the universe not just possible, but profoundly alive. Quantum gravity is one of the most ambitious quests in modern physics, a daring attempt to bridge two colossal pillars of science, quantum mechanics and general relativity. On one side, quantum mechanics governs the behavior of the smallest particles, revealing a world of probabilities, uncertainties, and flickering particles. On the other, general relativity describes the universe on its grandest scales, where massive objects warp space and time, creating the cosmic stage on which galaxies dance. Yet, despite their individual successes, these two theories don't play well together. They speak different languages, operate in different realms, and when pushed to extremes like inside a black hole or at the Big Bang, they break down entirely. This is where quantum gravity steps in, aiming to unify these seemingly incompatible frameworks into a single, coherent theory. The challenge of quantum gravity isn't just academic, it's fundamental to understanding the universe's hidden mechanisms. Take black holes, for example. At their cores lies a singularity, a point where gravity becomes infinitely strong and the rules of general relativity collapse. But quantum mechanics tells us that nothing in the universe can truly be infinite. There must be a smallest possible scale, a quantum limit. So, what happens when these two ideas collide? Quantum gravity seeks to answer that question, offering a new perspective where the fabric of space-time itself might be woven from tiny, discrete threads, like a cosmic tapestry made of individual stitches. One of the leading candidates in this quest is loop quantum gravity. This theory proposes that space isn't smooth and continuous, as Einstein's equations suggest, but instead is made up of tiny, indivisible loops. Picture space as a fabric, but instead of being woven from smooth threads, it's stitched together with tiny, interconnected rings. These loops create a kind of quantum foam at the smallest scales, where space-time becomes grainy and dynamic. Loop quantum gravity also suggests that singularities, like those at the center of black holes, might not be points of infinite density, but rather places where space-time flips, opening the door to entirely new possibilities, like the idea of a quantum bounce that could replace the Big Bang. Another contender in the race to unify quantum mechanics and gravity is string theory, which we touched on earlier. String theory takes a different approach, proposing that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings vibrate at different frequencies, giving rise to all the particles and forces we observe. But string theory goes even further, suggesting that space-time itself might have extra dimensions, hidden layers of reality that we can't perceive directly. These extra dimensions could hold the key to unifying gravity with the other fundamental forces, offering a glimpse of a deeper, more interconnected reality. Yet for all their elegance, these theories face significant challenges. One of the biggest hurdles is experimental verification. The scales at which quantum gravity operates are so small, far beyond what our current technology can probe, that testing these ideas directly is nearly impossible. Plus, the mathematics involved is incredibly complex, pushing the limits of human understanding. It's like trying to solve a puzzle with pieces that are too small to see and too intricate to handle. Despite these challenges, the pursuit of quantum gravity is more than just a scientific endeavor. It's a journey to the heart of reality itself. It's about uncovering the hidden mechanisms that weave the universe together, from the tiniest particles to the vastness of space-time. And while we may not have all the answers yet, the quest itself is a testament to humanity's curiosity and determination to understand the cosmos. As we explore these theories, we're reminded that the universe is a place of both mystery and wonder, where the smallest discoveries can lead to the grandest revelations. Quantum gravity isn't just about bridging the gap between two theories. It's about revealing the deeper harmony that underlies everything we see, and perhaps everything we don't. What if the universe isn't just a collection of particles and forces, but something deeply intertwined with the act of observation itself? What if consciousness, the very experience of being aware, plays a role in shaping the fabric of reality? This is one of the most provocative ideas in modern science, a concept that blurs the line between the observer and the observed, the mind and the cosmos. At the heart of this idea lies the observer effect in quantum mechanics. In the quantum world, particles don't have definite properties until they're measured. Take the famous double-slit experiment, for example. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, as if they're behaving like waves. But here's the twist. If you set up a detector to observe which slit the electron passes through, the interference pattern disappears. The mere act of observation seems to collapse the particle's wave-like behavior into a single, definite state. It's as if the universe waits for us to look before deciding how things should be. This phenomenon has led some physicists to suggest that consciousness might play a fundamental role in shaping reality. One of the most prominent voices in this debate was physicist John Wheeler, who proposed the participatory universe theory. In this view, the universe isn't a pre-existing entity, it's a work in progress, a cosmic story that's being written through the act of observation. Wheeler famously said, "We are participants in bringing into being not only the near and here but the far away and long ago." In other words, our observations might not just affect the present, they could influence the past too. But let's pause for a moment. Does this mean that consciousness literally creates reality? Not necessarily. While the observer effect is well documented, its interpretation is still hotly debated. Some scientists argue that the act of measurement, not consciousness itself, is what causes quantum systems to collapse. Others propose that consciousness might be a byproduct of the universe's complexity, rather than a driving force. This brings us to a fascinating question. How does consciousness connect to the broader cosmic order? If consciousness does play a role in shaping reality, could it also influence the large-scale structures of the universe, like galaxies and the cosmic web? Or is it limited to the realm of the very small, a quantum quirk with no bearing on the cosmos as a whole? Theories like quantum consciousness and panpsychism, the idea that consciousness is a fundamental property of matter, offer intriguing possibilities. Imagine if every particle in the universe had a tiny spark of awareness, and that these sparks combine to create the complex consciousness we experience. While this might sound like science fiction, it's a serious area of exploration for some physicists and philosophers, who see it as a potential bridge between the mind and the cosmos. As we ponder these ideas, we're reminded that the universe is a place of profound mystery. The role of consciousness in shaping reality, whether as an active participant or a passive observer, challenges us to rethink our place in the cosmos. It invites us to see ourselves not just as inhabitants of the universe, but as integral parts of its story, shaping and being shaped by the forces that govern existence itself. So, as we explore the connections between consciousness and cosmic order, we're not just asking scientific questions, we're delving into the very nature of what it means to be aware, to observe, and to exist. And in that exploration, we might just uncover a deeper truth about the universe, one that reveals the profound interplay between the mind and the cosmos. As we gaze up at the night sky, filled with countless stars and galaxies, one question lingers in the back of our minds: where is everyone? The universe is unimaginably vast, with billions of stars and planets scattered across its expanse. Given the sheer scale, it seems almost inevitable that intelligent life should exist somewhere out there. Yet, despite decades of searching, we've found no definitive evidence of extraterrestrial civilizations. This puzzling contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" To grasp the paradox, think of the universe as a cosmic desert. Imagine standing in the middle of an endless sandscape, where every grain of sand represents a star, and every oasis a potential home for life. With so many stars and planets, you'd expect to stumble across signs of life, footprints in the sand, remnants of a campfire, anything. But instead, the desert appears eerily silent, as if we're the only travelers wandering its vast expanse. So, why haven't we found any evidence of extraterrestrial civilizations? One possibility is that life is incredibly rare, a fragile spark that flickers into existence only under the most perfect conditions. Perhaps the universe is teeming with planets, but the journey from simple molecules to complex, intelligent life is so improbable that it's only happened once here on Earth. In this view, the cosmic desert isn't empty because life doesn't exist. It's empty because life is a cosmic fluke, a one in a trillion accident. Another explanation is that intelligent civilizations might be short-lived. Imagine a species that develops the technology to explore the stars, only to destroy itself through war, environmental collapse, or some other catastrophe. In this scenario, the desert isn't empty because life isn't there. It's empty because civilizations burn brightly but briefly, leaving behind only silence. But what if the answer lies not in the rarity of life or its fragility, but in our own limitations? The universe is vast, and the distances between stars are immense. Even if civilizations exist, they might be so far away that communication or travel is nearly impossible. It's like shouting into a canyon and hearing no echo, not because there's no one there, but because the canyon is just too big. The Fermi Paradox doesn't just challenge our search for extraterrestrial life. It also has profound implications for our understanding of the universe's hidden mechanisms. If life is rare, what does that say about the fine-tuning of the cosmos? If civilizations are fleeting, what does that reveal about the delicate balance between order and chaos? And if the universe is simply too vast for communication, what does that mean for our place within it? As we ponder these questions, we're reminded that the universe is a place of both wonder and mystery. The Fermi Paradox invites us to reflect not just on the possibility of life beyond Earth, but on the nature of existence itself. It challenges us to think bigger, to explore further, and to unravel the secrets that lie hidden in the cosmic desert. And in that exploration, we might just discover not only where everyone is, but who we are in the grand tapestry of the universe. In the vast silence of the cosmos, humanity has been listening, not just for echoes of the universe's origins, but for whispers of life beyond our own. This is the mission of SETI, the search for extraterrestrial intelligence, a scientific endeavor that has spent decades scanning the stars for signals that might hint at the presence of alien civilizations. It's a quest that's as daring as it is profound, seeking answers to one of the most compelling questions of all: are we alone? SETI's approach is rooted in the idea that advanced civilizations, if they exist, might communicate using electromagnetic signals, radio waves, lasers, or other forms of energy that can travel across the vast distances of space. Imagine tuning a cosmic radio, searching for a station broadcasting from another world. That's essentially what SETI does, using powerful telescopes and sophisticated algorithms to sift through the noise of the universe, hoping to catch a signal that stands out from the background hum of stars, pulsars, and cosmic static. One of the most famous moments in SETI history came in 1977, when a radio telescope in Ohio detected a signal so unusual that an astronomer circled it on the printout and wrote, "Wow." Next to it, the "wow" signal, as it's now known, lasted just 72 seconds and has never been detected again, leaving scientists to wonder whether it was a fleeting message from an alien civilization or simply a cosmic anomaly. To this day, it remains one of the most tantalizing and unresolved mysteries in the search for extraterrestrial intelligence. But SETI isn't just about waiting for a cosmic hello. It's also about understanding the universe's hidden mechanisms. By studying the patterns and properties of potential alien signals, scientists can learn more about the nature of communication, the evolution of technology, and even the limits of physics. For instance, how might a civilization encode information in a signal? Could their messages reveal insights into their understanding of the cosmos? And what would it mean if we discovered that other civilizations have faced the same challenges and questions that we have? Recent advances in technology have expanded SETI reach. Breakthrough Listen, for example, is one of the most ambitious SETI projects to date, using some of the world's most powerful telescopes to scan millions of stars for signs of intelligent life. It's also exploring new ways to detect signals, from searching for laser pulses to analyzing unusual patterns in starlight that might indicate the presence of advanced technology, like megastructures orbiting distant stars. Yet, despite these efforts, the universe remains silent, or at least it hasn't spoken in a way we can clearly understand. This leads to a deeper question. What does this silence tell us about the cosmos? Does it suggest that intelligent life is vanishingly rare, or that civilizations tend to self-destruct before they can communicate across the stars? Or could it mean that we're simply not listening in the right way or at the right time? SETI's search is more than just a scientific endeavor. It's a reflection of our own curiosity and our desire to understand our place in the universe. It challenges us to think beyond the boundaries of our own world, to imagine the possibilities of life in other forms, and to consider what the existence or absence of alien intelligence might reveal about the cosmos. As we continue to scan the skies, we're reminded that the universe is a place of endless mystery and wonder. SETI's search isn't just about finding others, it's about uncovering the deeper truths that connect us to the cosmos. And in that search, we might just discover not only who else is out there, but who we are in the grand tapestry of existence. What if we could take the vastness of the universe and boil it down into a single equation, a formula that could estimate the number of intelligent civilizations out there, waiting to be discovered? This is exactly what astronomer Frank Drake set out to do in the 1960s, crafting what's now known as the Drake equation. It's not just a mathematical tool, it's a framework for thinking about one of humanity's most profound questions: how common is life beyond Earth? The Drake equation is deceptively simple. It's a series of factors multiplied together, each representing a key piece of the puzzle. First, there's the rate at which stars form in our galaxy. Then, the fraction of those stars with planetary systems. Next, the number of planets in each system that could support life. After that, the likelihood of life actually emerging on those planets. From there, the equation considers the probability of that life evolving intelligence, developing the ability to communicate across space, and finally, how long such civilizations might last before fading into silence. At first glance, it might seem straightforward, but here's the catch. Many of these variables are still unknowns. We've made incredible strides in recent years, discovering thousands of exoplanets and learning more about the conditions that might make them habitable. But when it comes to life itself, how it starts, how often it arises, and whether it inevitably leads to intelligence, we're still in the dark. This uncertainty transforms the Drake equation from a precise calculator into a thought experiment, a way to explore the possibilities and challenges of finding life beyond Earth. So, what does the equation tell us? Depending on how you plug in the numbers, the results can vary wildly. Some estimates suggest there could be millions of intelligent civilizations scattered across the galaxy, while others hint that we might be the only ones. This range isn't just a reflection of our limited knowledge, it's a reminder of how much we still have to learn about the universe's hidden mechanisms. For instance, consider the factor that asks how long a civilization might last. This isn't just about technological longevity, it's about survival. Will a civilization destroy itself through war or environmental collapse, or will it find a way to thrive and endure? This variable ties the Drake equation to broader questions about the nature of life and the delicate balance between order and chaos. The same balance we see at play in quantum turbulence, cosmic inflation, and the evolution of galaxies. The Drake equation doesn't just give us a number, it invites us to think deeply about the universe and our place within it. It challenges us to consider whether life is a rare, fragile phenomenon or a common thread woven into the fabric of the cosmos. And as we explore these questions, we're reminded that the search for extraterrestrial intelligence isn't just about finding others, it's about understanding ourselves. This equation is more than a mathematical exercise. It's a bridge between the known and the unknown, the microscopic and the cosmic. It connects the flicker of quantum particles to the vastness of the universe, hinting at the hidden mechanisms that might one day reveal whether we're truly alone or part of a much larger cosmic community. As we continue to refine our understanding of these variables, we're not just solving an equation, we're unraveling the mysteries of existence itself. Throughout the history of the cosmos, countless forces have shaped the universe's gravity, entropy, quantum fluctuations, and more. But now, a new force has entered the cosmic stage: humanity. For the first time, a species has emerged with the ability to not only observe the universe but to actively alter it. This era, often referred to as the Anthropocene, marks a turning point where human activity begins to leave its imprint not just on Earth, but on the cosmos itself. From the satellites orbiting our planet to the probes venturing into the depths of space, we are becoming architects of our own cosmic story. Take space exploration, for example. In just a few decades, we've gone from launching our first satellite to sending spacecraft beyond the edges of our solar system. Voyager 1, now drifting in interstellar space, carries a golden record filled with sounds and images of Earth, a message to any future discoverers about who we are and where we came from. But our reach extends even further. Rovers like Curiosity and Perseverance are exploring Mars, searching for signs of ancient life and paving the way for potential human colonization. These missions aren't just scientific endeavors, they're the first steps in humanity's quest to become a multi-planetary species. Yet, with this progress comes a new challenge: space debris. Thousands of defunct satellites, spent rocket stages, and fragments from collisions now orbit Earth, creating a growing hazard for active spacecraft and future missions. This ever-expanding cloud of debris is a stark reminder of our impact, a cosmic footprint that could one day hinder our ability to explore beyond our planet. It's a paradox of our ingenuity. The same technology that allows us to reach the stars also risks closing the door behind us. But what if we could do more than just explore? What if we could reshape entire worlds, terraforming the process of altering a planet's environment to make it habitable for humans has long been a dream of science fiction. Mars, with its thin atmosphere and frozen water, is often seen as the most viable candidate. Imagine transforming its barren, rust-colored surface into a lush, Earth-like world, complete with breathable air and flowing rivers. While this vision is still far from reality, the idea raises profound questions about humanity's role in the universe. Are we destined to be caretakers of other worlds, or will our presence disrupt the delicate balance of cosmic order? These questions go beyond the practicalities of space travel and colonization. They touch on something deeper, our place in the universe's hidden mechanisms. For billions of years, the cosmos has evolved through natural processes, driven by laws that we are only beginning to understand. Now, as we step into the role of cosmic engineers, we must ask ourselves, are we enhancing the universe's potential, or are we introducing a new form of chaos? The Anthropocene isn't just about humanity's impact on Earth, it's about our growing influence on the cosmos itself. As we venture further into space, we carry with us the hopes and challenges of a species striving to understand its place in the grand tapestry of existence. Whether we're launching satellites, cleaning up space debris, or dreaming of terraforming Mars, we are shaping a future that could redefine our relationship with the universe. In this new era, the question isn't just what the universe can teach us, it's what we, as a species, can contribute to its unfolding story. As we navigate this uncharted territory, we're reminded that the cosmos is not just a stage for us to observe, it's a canvas on which we are beginning to leave our mark. And in that mark, we might just find the answer to one of humanity's most profound questions. What is our role in the hidden mechanisms of the universe? As we stand on the brink of a new era in space exploration, the possibilities stretch before us like an uncharted cosmic frontier. The next chapter of humanity's journey into the stars promises not just to expand our reach, but to deepen our understanding of the universe's hidden mechanisms. From cutting-edge telescopes that peer deeper into the cosmos than ever before to bold plans for interstellar travel, the future of space exploration is a tapestry of ambition, discovery, and innovation. Imagine a telescope so powerful it can capture the faintest whispers of light from the earliest moments of the universe. This is the promise of the James Webb Space Telescope and its successors. These instruments are not just tools for observation, they're time machines, allowing us to look back billions of years to witness the birth of galaxies, the formation of stars, and the emergence of the cosmic web. With each new discovery, we're peeling back layers of the universe's history, uncovering clues about the forces that shaped it and the mysteries that still lie hidden. But our ambitions don't stop at observation. The dream of interstellar travel, once confined to the pages of science fiction, is now a tangible goal. Projects like Breakthrough Starshot aim to send tiny, laser-propelled probes to nearby star systems, traveling at a fraction of the speed of light. These missions could provide our first close-up look at exoplanets, potentially revealing signs of life or even habitable worlds. It's a vision that pushes the boundaries of what we thought possible, transforming the stars from distant points of light into destinations within our reach. Yet, the journey to the stars isn't just about technology, it's about our place in the cosmos. As we venture further into space, we're not just explorers, we're stewards of a fragile, interconnected universe. The challenges we face, from the ethical implications of space colonization to the environmental impact of space debris, remind us that our actions have consequences not just for Earth, but for the cosmos as a whole. How we navigate these challenges will shape not only our future, but the future of the universe itself. This duality of discovery and responsibility defines the next chapter of space exploration. It's a journey that will test our ingenuity, our resilience, and our understanding of what it means to be human. Whether we're peering into the depths of the universe or sending probes to distant stars, we're not just uncovering the hidden mechanisms of the cosmos, we're becoming active participants in its unfolding story. And as we look to the future, one thing becomes clear: the universe is not just a place to explore, it's a canvas on which we are beginning to write our own chapter. The discoveries we make, the technologies we develop, and the choices we take will shape not just our destiny, but the destiny of the cosmos. In this grand adventure, we are both explorers and architects, shaping a future that reaches far beyond the stars. So, as we stand on the edge of this cosmic frontier, let's not just ask what lies ahead, let's ask how we can explore it with curiosity, wisdom, and respect. The universe is waiting, and its secrets are ours to uncover. Mathematics is often called the language of the universe, and for good reason. It's the tool that allows us to translate the chaotic beauty of the cosmos into something we can understand, predict, and even manipulate. From the graceful spirals of galaxies to the intricate dance of subatomic particles, mathematics provides the framework that reveals the hidden order beneath the surface. It's as if the universe speaks in equations, and we've been slowly learning to listen. Take Einstein's theory of general relativity, for example. This groundbreaking theory, expressed through a series of elegant equations, describes how gravity works not as a force but as the curvature of space-time. Imagine placing a bowling ball on a trampoline. The way it warps the fabric is a simple analogy for how massive objects like stars and planets bend the fabric of the universe. But without the precise language of mathematics, this profound insight into gravity's true nature would remain hidden, locked away in the abstract. Or consider fractal geometry, the study of infinitely complex patterns that repeat at every scale. Fractals are everywhere in nature, in the branching of trees, the shape of coastlines, and even the structure of our lungs. But they're also found in the cosmos, in the way galaxies cluster along filaments of the cosmic web, or in the turbulent swirls of quantum fields. Mathematics gives us the tools to describe these patterns, revealing a deep connection between the microscopic and the macroscopic. But math isn't just a passive observer of the universe, it's an active participant in uncovering its secrets. When scientists discovered the Higgs boson, it wasn't through direct observation, it was through the predictions of mathematical models. The equations pointed the way, guiding physicists to the exact energy levels where the elusive particle would appear. It's as if mathematics acts as a cosmic map, showing us where to look and what to expect, even in the most uncharted territories. What's truly remarkable is how mathematics bridges the gap between chaos and order. At first glance, the universe might seem like a chaotic mess, with particles flickering unpredictably and galaxies colliding in violent bursts. But beneath the surface, there's a hidden symmetry, a mathematical harmony that ties everything together. From the Fibonacci sequence in sunflower seeds to the golden ratio in spiral galaxies, mathematics reveals the underlying patterns that make the universe not just random, but beautifully organized. So, what does this mean for our understanding of cosmic order? Mathematics doesn't just describe the universe, it helps us see it as a unified whole. It connects the quantum realm to the cosmos, the tiniest particles to the largest structures, showing us that the same laws apply at every scale. Whether we're calculating the trajectory of a comet or mapping the curvature of space-time, mathematics is the thread that weaves the universe's story together. As we continue to explore the cosmos, mathematics remains our most powerful tool, guiding us through the mysteries of existence with clarity and precision. It's a reminder that the universe, for all its complexity, operates according to rules we can understand, and that, with the right equations, we might just uncover the deepest truths of all. The universe is more than just a collection of stars, galaxies, and particles. It's a stage where some of the most profound questions about existence are played out. Beyond the equations and observations, cosmology invites us to ask the big questions. What is the nature of reality? Does the universe have a purpose? And what does it mean to exist within it? These questions might seem abstract, but they're deeply tied to the hidden mechanisms we've been exploring, from quantum turbulence to the cosmic web. Take the nature of reality, for example. Philosophers have pondered this for millennia, but modern science offers a unique lens. Quantum mechanics tells us that particles exist in a haze of probabilities, only collapsing into definite states when observed. Does this mean reality itself is shaped by observation? As physicist John Wheeler once said, "We are participants in bringing into being not only the near and here but the far away and long ago." This idea that the universe might be a participatory phenomenon challenges our understanding of what's real and what's possible. Then there's the question of purpose. Does the universe have one, or is it simply the product of random chance? Some scientists argue that the fine-tuning of the universe's constants, those precise values that allow for life, suggests a deeper design. Others see it as a cosmic coincidence, a result of the multiverse where countless universes exist, each with its own set of laws. Philosopher Immanuel Kant once wrote, "Two things fill the mind with ever-increasing wonder and awe, the starry heavens above me and the moral law within me." This duality of the cosmic and the personal reminds us that questions of purpose aren't just scientific, they're deeply human. These philosophical inquiries aren't just idle musings, they're essential to understanding the hidden mechanisms of the universe. For instance, the quest to unify quantum mechanics and general relativity isn't just about finding the right equations, it's about uncovering the fundamental nature of space, time, and existence itself. As physicist Carlo Rovelli puts it, reality is not what it seems. The more we learn, the more we realize how little we know. The intersection of science and philosophy is where curiosity meets wonder. It's where the tools of observation and experimentation meet the timeless questions that have driven human thought for centuries. And in this meeting, we find a richer, more nuanced understanding of the cosmos, one that embraces both the measurable and the metaphysical. So, as we continue to explore the universe's hidden mechanisms, let's not forget to ask the big questions. They remind us that science isn't just about answers. It's about the journey of discovery, the pursuit of understanding, and the awe of standing before the infinite. In the words of Carl Sagan, somewhere, something incredible is waiting to be known, and perhaps in asking these questions, we come one step closer to knowing it. As we journey deeper into the cosmos, uncovering its hidden mechanisms, one thing becomes increasingly clear: there are limits to what we can know. For all our ingenuity and curiosity, the universe holds mysteries that may forever remain beyond our grasp. These boundaries of understanding aren't just gaps in our knowledge, they are fundamental barriers woven into the fabric of reality itself. Consider the Planck scale, the smallest measurable unit in the universe. At this unimaginably tiny level, space and time lose their smooth, continuous nature, becoming a frothy, chaotic quantum foam. It's a realm where the rules of physics as we know them break down, where gravity and quantum mechanics collide in ways we can't yet comprehend. The Planck length, about 1/1,000,000,000 of a trillionth the size of an atom, represents a frontier beyond which our current theories simply don't apply. To explore this scale, we'd need particle accelerators the size of galaxies, a feat far beyond our technological capabilities. Then there's the multiverse, a concept that stretches the limits of our imagination. If our universe is just one of countless others, each with its own set of physical laws, how could we ever observe or interact with them? The idea of parallel universes, while mathematically plausible, remains firmly in the realm of theory. Even if they exist, the sheer scale and separation of these universes might place them forever beyond our reach. What about the nature of consciousness? While science has made incredible strides in understanding the brain, the essence of awareness, why we experience the world as we do, remains one of the greatest enigmas. Is consciousness a byproduct of physical processes, or something more fundamental, woven into the very fabric of reality? These questions challenge not just our understanding of the mind, but our understanding of existence itself. And let's not forget the ultimate question: what lies beyond the observable universe, the cosmos we can see, illuminated by the light of stars and galaxies, is just a tiny fraction of what's out there. Beyond the cosmic horizon, space continues to expand, carrying with it regions we may never be able to observe or understand. What exists in those distant realms? Are there other universes, other realities, or is there simply nothing at all? These mysteries remind us of the humility inherent in scientific inquiry. For all our progress, we are still explorers standing at the edge of a vast, uncharted frontier. The more we learn, the more we realize how much we don't know. And yet, this uncertainty isn't a cause for despair, it's a source of wonder and inspiration. It drives us to keep asking questions, to keep searching, even when the answers seem out of reach. In the end, the limits of human understanding aren't just barriers, they're invitations. They remind us that the universe is far stranger and more complex than we can imagine, and that the pursuit of knowledge is a journey without end. As we continue to explore, we're not just uncovering the secrets of the cosmos, we're discovering the boundless potential of our own curiosity. And in that discovery, we find not just answers, but the joy of asking the questions that keep us reaching for the stars. Technology has always been our bridge to the cosmos, transforming distant stars and abstract theories into something tangible and understandable. Over the centuries, every leap in technological innovation has brought us closer to unraveling the universe's deepest secrets. From the first crude telescopes that revealed the moons of Jupiter to the colossal particle accelerators that peer into the heart of matter, each tool has expanded our understanding in ways that were once unimaginable. Today, we stand at the forefront of a new era where cutting-edge technology is unlocking mysteries that have puzzled humanity for generations. Take the James Webb Space Telescope, for example. Launched in December 2021, this marvel of engineering has already reshaped our view of the cosmos. With its massive gold-coated mirror and infrared capabilities, Webb can peer through cosmic dust and gas, capturing light from the universe's earliest galaxies. These images aren't just breathtaking, they're windows into the past, revealing how the first stars and galaxies formed billions of years ago. Webb has also detected water vapor in the atmospheres of distant exoplanets, offering tantalizing hints about the potential for life beyond our solar system. It's a reminder that the tools we build aren't just extensions of our curiosity, they are keys to unlocking the universe's hidden mechanisms, but telescopes are only one piece of the puzzle. On Earth, particle accelerators like the Large Hadron Collider are pushing the boundaries of what we know about the quantum realm. By smashing particles together at nearly the speed of light, these machines recreate conditions that existed just moments after the Big Bang. In 2012, the LHC confirmed the existence of the Higgs boson, a particle that gives mass to other particles and completes the standard model of physics. This discovery wasn't just a scientific triumph. It was a testament to how technology can illuminate the fundamental building blocks of reality. And then there's the rise of artificial intelligence and machine learning, which are transforming how we process and interpret the vast amounts of data generated by these instruments. Algorithms can now sift through millions of star systems, identifying exoplanets or detecting subtle patterns in cosmic radiation that human eyes might miss. These tools are helping us see the universe in new ways, revealing connections and insights that were once buried in noise. What's truly exciting is the potential of future technologies. Imagine quantum computers capable of simulating the universe's most complex systems, or space-based interferometers that can detect gravitational waves from the earliest moments of creation. These advancements could answer questions we haven't even thought to ask yet, questions about the nature of dark matter, the origins of space-time, or the possibility of parallel universes. As we continue to push the boundaries of what's possible, one thing becomes clear: technology isn't just a tool for discovery, it's a reflection of our creativity and determination to understand the cosmos. With every innovation, we're not just uncovering new secrets, we're redefining what it means to explore the universe. And in that exploration, we're reminded that the cosmos is not just a place to observe, it's a story to be written, one breakthrough at a time. As humanity reaches further into the cosmos, venturing beyond our planet with ever-growing ambition, a crucial question emerges: what responsibilities come with this progress? Space exploration isn't just about scientific discovery or technological achievement, it's also about grappling with profound ethical questions. How do we balance our drive to explore with the need to protect what we leave behind, both on Earth and in the stars? These considerations aren't just philosophical, they're deeply tied to our understanding of cosmic order and humanity's place within it. One of the most pressing ethical dilemmas is the environmental impact of space exploration. Rockets launch with immense force, releasing gases and particles into the atmosphere that can contribute to climate change and ozone depletion. Space debris, the discarded remnants of satellites and spacecraft, now orbits Earth in a growing cloud, posing risks to future missions and even the International Space Station. The question isn't just how we explore space, it's how we do so without harming the very planet that makes our exploration possible. But the ethical considerations don't stop at Earth's atmosphere. As we set our sights on other worlds, like Mars or the Moon, we must ask, do we have the right to alter these environments? Terraforming, the process of making a planet habitable for humans, is a tantalizing idea, but it raises concerns about the potential destruction of alien ecosystems, if they exist. Imagine discovering microbial life on Mars, only to unintentionally wipe it out in our quest to colonize the planet. What responsibilities do we have to preserve the cosmic environment, even as we seek to expand our horizons? Cultural preservation is another dimension of this ethical puzzle. Space exploration is often framed as a global endeavor, but the reality is more complex. Historically, space missions have been dominated by a handful of nations, raising questions about equity and access. Who gets to explore space and who benefits from its resources? As private companies like SpaceX and Blue Origin play an increasingly prominent role, the line between public and private interests becomes blurred. Should the cosmos be treated as a shared heritage, or as a frontier open to exploitation by those with the means to reach it? These questions aren't just about the present, they are about the future. Every decision we make today shapes the legacy we leave for generations to come. Will humanity's expansion into space be marked by cooperation and stewardship, or by conflict and exploitation? The answers we find will not only define our relationship with the cosmos, but also reveal deeper truths about who we are as a species. Reflecting on these ethical challenges brings us back to the broader theme of cosmic order. The universe operates according to intricate laws and balances, from the gravitational dance of galaxies to the quantum flicker of particles. As we venture into space, we're not just observers of this order, we're participants. The choices we make, the responsibilities we embrace, and the values we uphold will determine whether we harmonize with the cosmos or disrupt its delicate equilibrium. So, as we stand on the threshold of a new era in space exploration, let's not just ask what we can achieve, let's ask how we can achieve it responsibly. The universe is vast, but it's also interconnected, and our actions ripple across its fabric. In balancing progress with responsibility, we're not just exploring space, we're exploring what it means to be stewards of existence itself. The universe has always been a source of inspiration, not just for scientists but for artists, musicians, and creators of all kinds. While science gives us the tools to measure and understand the cosmos, art offers a different kind of lens, one that translates the vast, often abstract beauty of the universe into something deeply personal and emotionally resonant. From the haunting melodies of space-inspired music to the vivid brushstrokes of cosmic paintings, art allows us to connect with the cosmos in ways that equations and data alone cannot. Take the work of composer Gustav Holst, for example. His orchestral suite, The Planets, is more than just a musical masterpiece. It's a journey through the solar system, with each movement capturing the character and mythology of a planet. Mars, the bringer of war, thunders with ominous percussion, while Neptune, the mystic, drifts into ethereal, otherworldly tones. Holst didn't just write music, he created an auditory bridge between the human experience and the celestial realm, reminding us that the cosmos isn't just a place of numbers and laws, but of stories and emotions. Visual artists, too, have long been captivated by the mysteries of the universe. Consider the works of Vincent van Gogh, whose iconic Starry Night swirls with vibrant blues and golds, capturing the turbulence and beauty of the night sky. Van Gogh once wrote, "I don't know anything with certainty, but seeing the stars makes me dream." His painting isn't just a depiction of the heavens, it's an expression of how the cosmos stirs something deep within us, a sense of wonder, curiosity, and even longing. Even modern artists continue to draw inspiration from the cosmos. Digital creators like NAS own visualizers transform raw data from telescopes into breathtaking animations and images. The Pillars of Creation, a towering structure of gas and dust captured by the Hubble Space Telescope, has become not just a scientific marvel but a cultural icon, inspiring everything from album covers to poetry. These visualizations remind us that science and art aren't separate endeavors, they are two sides of the same coin, each offering a unique way to explore and interpret the universe. Music, too, has evolved alongside our understanding of space. Composers like John Williams, with his iconic Star Wars scores, and electronic artists like Jean Mitchell Jarre, with his album Oxygen, have used sound to evoke the vastness and mystery of the cosmos. Even the Voyager Golden Record, a time capsule of Earth's sounds and music sent into interstellar space, is a testament to how art can serve as a universal language, bridging the gap between worlds and civilizations. What's fascinating is how art and science often intersect, enriching each other in unexpected ways. As physicist and novelist Alan Lightman once said, "Science and art are two ways of looking at the world, and both are necessary for understanding." Artists bring a sense of wonder and imagination to the cosmos, while scientists provide the framework and tools to explore it. Together, they create a fuller picture of the universe, one that speaks not just to our minds, but to our hearts. So, as we marvel at the universe's hidden mechanisms, let's not forget the role of art in helping us make sense of it all. Whether through a symphony, a painting, or a poem, art reminds us that the cosmos isn't just something to study, it's something to feel, to dream about, and to be inspired by. In the end, the universe is not just a place of discovery, it's a canvas for creativity, inviting us to see it not just as it is, but as it could be. What propels humanity to look beyond the horizon, to question the unknown, and to venture into the vastness of the cosmos? The answer lies in something deeply human: curiosity. It's the spark that ignites our desire to explore, to understand, and to connect the dots between the seen and the unseen. From the earliest astronomers charting the stars to modern scientists probing the quantum realm, curiosity has been the driving force behind humanity's relentless quest for knowledge. Think about the ancient Greeks who gazed at the night sky and wondered about the nature of the heavens. With no telescopes or advanced tools, they relied on observation and imagination to map the movements of planets and stars. Their curiosity laid the foundation for centuries of astronomical discovery, proving that even the simplest questions, like "Why do the stars move?" can lead to profound insights. Fast forward to the Renaissance, and curiosity took on new dimensions. Galileo, armed with a rudimentary telescope, turned his lens toward the heavens and discovered the moons of Jupiter. This wasn't just a scientific breakthrough, it was a testament to the power of curiosity to challenge established beliefs and expand our understanding of the universe. Galileo's discoveries didn't just change science, they changed how we see ourselves in the cosmos, shifting humanity from the center of the universe to a small part of a much larger story. In the modern era, curiosity continues to push the boundaries of what we know. Take the search for gravitational waves, for example. A century ago, Einstein predicted these ripples in space-time, but it took decades of curiosity-driven research to detect them. In 2015, the LIGO Observatory finally captured the faint echoes of two black holes colliding, confirming Einstein's theory and opening a new window into the universe. This discovery wasn't just about proving a hypothesis, it was about satisfying a deep, human need to understand the hidden mechanisms that govern reality. Curiosity doesn't just fuel scientific breakthroughs, it shapes the way we approach the unknown. Consider the field of astrobiology, which seeks to answer the question, are we alone in the universe? From studying extremophiles in Earth's most hostile environments to analyzing the atmospheres of distant exoplanets, scientists are driven by a simple yet profound curiosity. What does it mean to be alive? This question doesn't just guide research, it reminds us that the pursuit of knowledge is as much about exploring the universe as it is about exploring ourselves. So, what makes curiosity so powerful? It's not just the desire to know, it's the courage to ask questions even when the answers are unclear. It's the willingness to embrace uncertainty and to see the unknown not as a barrier, but as an invitation. Curiosity transforms the cosmos from a distant, impersonal expanse into a place of wonder and possibility, a stage where humanity's greatest stories are written. As we reflect on the role of curiosity in uncovering the universe's hidden mechanisms, we're reminded that it's not just a tool for discovery, it's a reflection of who we are. It's the thread that connects the past, present, and future of human exploration, weaving together the stories of those who dared to ask, "What if?" And in that thread, we find not just the answers we seek, but the inspiration to keep searching, keep wondering, and keep reaching for the stars. The universe is vast, and its mysteries are endless, but humanity's greatest breakthroughs often come not from lone geniuses toiling in isolation, but from the collective effort of minds working together. Collaboration across disciplines, cultures, and borders has been the engine driving some of the most profound discoveries in science, revealing the hidden mechanisms of the cosmos in ways no single individual could achieve alone. Consider the International Space Station, a marvel of engineering and cooperation, built and maintained by space agencies from the United States, Russia, Europe, Japan, and Canada. The ISS is more than just a laboratory orbiting Earth. It's a symbol of what humanity can accomplish when we work together. Astronauts from different nations live and conduct experiments side by side, sharing knowledge and resources to advance our understanding of space, biology, and physics. As former NASA astronaut Scott Kelly once said, "The space station is a testament to what we can do when we put aside our differences and focus on a common goal." But collaboration isn't limited to space missions. Take the field of astrophysics, where researchers from diverse backgrounds, mathematicians, computer scientists, engineers, and physicists come together to tackle questions about the universe's origins. The Event Horizon Telescope project, which captured the first image of a black hole in 2019, is a prime example. This global effort involved over 200 scientists from 20 countries, combining data from telescopes around the world to create a virtual observatory the size of Earth. The result, a groundbreaking image that confirmed Einstein's predictions and opened new doors for understanding gravity and space-time. Interdisciplinary collaboration also plays a crucial role in uncovering the universe's secrets. For instance, the study of quantum mechanics has benefited from the insights of chemists, who explore how particles interact at the molecular level, and computer scientists, who develop algorithms to simulate quantum systems. Similarly, cosmologists and particle physicists often work hand in hand, using particle accelerators to recreate the conditions of the early universe and test theories about its evolution. As physicist Carlo Rovelli aptly put it, science is a collective enterprise, a conversation across generations and disciplines, where each contribution builds on the work of others. The power of collaboration extends beyond scientific discovery. It also fosters innovation and resilience. When researchers combine their expertise, they can approach problems from multiple angles, finding solutions that might otherwise remain hidden. This spirit of teamwork is especially vital in tackling global challenges, from climate change to space exploration, where the stakes are high and the questions are complex. Reflecting on the role of collaboration in science, we're reminded that the pursuit of knowledge is a shared journey. No single person, field, or nation holds all the answers. It's through the collective effort of curious minds, working together across boundaries, that we uncover the universe's hidden mechanisms and chart a path toward a deeper understanding of existence itself. So, as we marvel at the wonders of the cosmos, let's also celebrate the connections that make discovery possible. The universe may be vast and mysterious, but through collaboration, we're proving that humanity's greatest strength lies in our ability to unite, explore, and uncover the truths that bind us all. The mysteries of space have always captivated the human imagination, not just in the realm of science, but in the stories we tell and the art we create. From the silver screen to the pages of novels, space has become a canvas for exploring the unknown, sparking curiosity, and reflecting on our place in the cosmos. It's no wonder that space mysteries have become a cornerstone of popular culture, shaping how we think about the universe and ourselves. Take science fiction films, for example. Movies like Interstellar and Gravity don't just entertain, they immerse us in the challenges and wonders of space exploration. Interstellar delves into the mind-bending concepts of time dilation and black holes, weaving complex science into a deeply human story about love and survival. Meanwhile, Gravity captures the visceral isolation of space, reminding us of the fragility of life and the vastness of the void. These films don't just depict space, they invite us to feel its awe and mystery, making the cosmos a character in its own right. Books, too, have long been a medium for exploring space mysteries. H.G. Wells' The War of the Worlds imagined an invasion from Mars, blending scientific speculation with social commentary. More recently, Andy Weir's The Martian turned the harsh realities of space travel into a gripping tale of ingenuity and resilience. These stories don't just entertain, they inspire us to ask questions. What would it be like to live on another planet? How would we confront the unknown? By posing these questions, space-themed literature fuels our curiosity and pushes us to dream bigger. Even in music and visual art, space has left its mark. David Bowie's Space Oddity captured the loneliness and wonder of an astronaut adrift in the cosmos, while album covers like Pink Floyd's Dark Side of the Moon used space imagery to evoke a sense of mystery and introspection. Artists like Yayoi Kusama have used cosmic themes to explore infinity and the human connection to the universe, reminding us that space isn't just a place, it's a metaphor for the infinite possibilities of existence. What's truly remarkable is how these cultural expressions influence public interest in space exploration. A film like Apollo 13 reignited fascination with the moon landings, while TV shows like Star Trek and The Expanse have inspired generations to pursue careers in science and engineering. These stories don't just reflect our curiosity about the cosmos, they amplify it, turning abstract ideas into relatable narratives that resonate with audiences of all ages. The cultural impact of space mysteries goes even deeper. They remind us that exploration isn't just about discovering new worlds, it's about discovering ourselves. By imagining life on other planets, confronting the challenges of space travel, or grappling with the vastness of the universe, we're forced to reflect on what it means to be human. Are we alone? What's our purpose? These are questions that science alone can't answer, but through art and storytelling, we can explore them in ways that are both profound and deeply personal. As we look to the future, the interplay between space mysteries and popular culture will continue to inspire and challenge us. Whether through a blockbuster film, a thought-provoking novel, or a haunting piece of music, these cultural expressions remind us that the cosmos is not just a place of discovery, it's a source of endless wonder. And in that wonder, we find not just the mysteries of the universe, but the stories that connect us all. What if the key to unlocking the universe's greatest mysteries lies not in a telescope or a particle accelerator, but in a classroom? Education has always been the foundation of discovery, the spark that ignites curiosity and transforms it into knowledge. From the earliest days of human exploration to the cutting-edge research of today, the desire to understand the cosmos has been nurtured by teachers, mentors, and programs that inspire the next generation of explorers. Take space camps, for example. These immersive programs give young people a taste of what it's like to be an astronaut, engineer, or scientist, they don't just teach facts, they create experiences. Imagine a group of kids strapping into a simulator, feeling the rumble of a rocket launch, or designing their own Mars rover. These moments aren't just fun, they're transformative, planting seeds of curiosity that can grow into lifelong passions. Space camps are more than just extracurricular activities, they are incubators for future innovators, places where dreams of exploring the stars begin to take shape. Science outreach programs play a similar role, bringing the wonders of the universe to communities that might not otherwise have access. Organizations like NASA, a science activation, or the European Space Agency's educational initiatives work to bridge the gap between cutting-edge research and everyday learning. They provide resources, workshops, and hands-on activities that make science tangible and exciting. Whether it's a classroom building a model satellite or a student analyzing real data from a space telescope, these programs show that science isn't just something you read about, it's something you do. The impact of these efforts is undeniable. Consider the story of high school student Wolf Cuckier, who discovered a new planet during a summer internship at NASA. Using data from the test satellite, Cuckier identified a system with 2 stars and a planet orbiting them, a remarkable find for any scientist, let alone a teenager. His story is a testament to the power of education and mentorship, showing that curiosity, when nurtured, can lead to extraordinary discoveries. But education isn't just about individual achievements, it's about building a community of thinkers and explorers. When students come together to solve problems, whether in a classroom, a lab, or a virtual collaboration, they learn not just about science, but about teamwork and resilience. These skills are essential for tackling the challenges of space exploration, from designing spacecraft to interpreting data from distant galaxies. As we look to the future, the role of education becomes even more critical. The next generation of explorers will face questions we can't yet imagine, from understanding dark energy to searching for life on distant worlds. They'll need not just knowledge, but creativity, adaptability, and a deep sense of curiosity. And that's where education comes in, not just as a way to pass on what we know, but as a way to inspire what we don't yet understand. So, as we celebrate the achievements of today's scientists and explorers, let's also invest in the dreamers of tomorrow. Whether through a space camp, a classroom experiment, or a mentorship program, every moment of learning is a step toward the stars. And in those steps, we find not just the future of exploration, but the enduring power of curiosity to light the way. As we uncover the hidden mechanisms of the universe, from the chaotic whirl of quantum turbulence to the majestic order of galaxies, we're not just learning about the cosmos, we're learning about ourselves. The universe, in all its vastness and complexity, acts as a mirror, reflecting back profound truths about humanity's place within it. What does it mean to exist in a universe governed by laws we can barely comprehend? How do we reconcile our fleeting existence with the timeless dance of stars and galaxies? These questions aren't just philosophical, they're deeply tied to the essence of what it means to be human. One of the most humbling realizations that astronomy offers is the sheer scale of the cosmos. Our planet, our solar system, even our galaxy, are all but tiny specks in an unimaginably vast expanse. This perspective isn't meant to diminish our significance, rather, it invites us to embrace humility. In the grand tapestry of the universe, we are both insignificant and extraordinary, small in scale, yet capable of asking the biggest questions. As Carl Sagan famously put it, we are a way for the cosmos to know itself. This duality, of being both a part of the universe and an observer of it, challenges us to see our place not as separate from the cosmos, but as deeply interconnected with it. This interconnectedness extends beyond the physical. The same laws that govern the formation of stars and galaxies also shape the atoms in our bodies. The carbon in our cells, the oxygen we breathe, these elements were forged in the hearts of ancient stars, scattered across the cosmos in supernova explosions, and eventually gathered here on Earth to form life. When we look at the stars, we're not just gazing at distant lights, we're seeing the very origins of our existence. This realization transforms the cosmos from a distant, impersonal expanse into a shared story, one in which we are both participants and storytellers. But what does this interconnectedness mean for our sense of purpose? If the universe operates without a predetermined goal, does that mean our lives are without meaning? On the contrary, the absence of cosmic purpose might be the very thing that empowers us to create our own. In a universe driven by chaos and order, we have the unique ability to shape our destinies, to find meaning in the connections we forge and the questions we ask. The universe doesn't hand us answers, it invites us to seek them, to explore, to wonder. This journey of discovery isn't just about understanding the cosmos, it's about understanding ourselves. As we peer into the depths of space and the intricacies of the quantum realm, we're reminded that the universe is not just a place of mystery, it's a reflection of our own curiosity, resilience, and creativity. The same forces that shaped galaxies and stars also shape the human spirit, driving us to explore, to create, and to connect. As we prepare to conclude this exploration of the universe's hidden mechanisms, let's take a moment to reflect on what we've learned. The cosmos is vast and mysterious, but it's also deeply personal, a mirror that reveals not just the secrets of existence, but the potential within each of us. Whether through the lens of science, philosophy, or art, the universe invites us to see ourselves not as isolated beings, but as integral parts of a grand, interconnected whole. So, as we look to the stars, let's not just see them as distant lights, let's see them as reminders of our shared journey, our shared story, and the endless possibilities that lie ahead. The universe may be vast, but it's also a place of wonder, waiting for us to explore, to understand, and to find our place within it. From the unpredictable swirls of quantum turbulence to the vast, ordered spirals of galaxies, our journey through the hidden mechanisms of the universe has revealed a profound truth. Chaos and harmony are not opposites, they are partners in the cosmic dance. At every scale, from the tiniest particles to the grandest structures, we've seen how disorder gives rise to order, and how the universe's most chaotic moments often lay the groundwork for its most beautiful patterns. Think about it. The quantum fluctuations that once seemed like random noise turned out to be the seeds of galaxies, stars, and planets. The same forces that create turbulence in a superfluid helium experiment might echo in the swirling arms of a galaxy light years away. Even the cosmic web, that sprawling network of filaments and voids, feels like a reflection of the quantum world on a colossal scale. These connections remind us that the universe is not a collection of separate phenomena, it's a unified whole where the smallest and largest scales are intimately linked. But what does this mean for us? As we uncover these hidden mechanisms, we're not just learning about the cosmos, we're learning about the delicate balance that defines existence itself. The universe is a place where chaos and order coexist, where randomness and structure intertwine to create the complexity we see around us. And in that interplay, we find a deeper truth, that the universe is not just something to observe, it's something to marvel at, to question, and to explore. So, as we bring this journey to a close, let's take a moment to reflect on the wonder of it all. The universe is not just a place of stars and galaxies. It's a story of connections, a tapestry woven from the threads of chaos and harmony. It invites us to keep asking questions, to keep searching for answers, and to embrace the mystery that makes science so endlessly fascinating. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Whether you're a seasoned space enthusiast or just beginning to explore the cosmos, the universe has something to offer everyone. So, what's next for you? What mysteries are you curious to uncover? Share your thoughts in the comments below, and don't forget to subscribe for more journeys into the wonders of the cosmos. Together, let's keep exploring, learning, and marveling at the universe's endless secrets. Thank you for joining us on this adventure, wherever the cosmos takes you next. Remember, the universe is not just out there, it's within us, waiting to be